Hello everyone and welcome to week 6 of the class. I hope y'all enjoyed learning to identify igneous rocks in lab last week and that was extremely informative and a good supplement to the lecture portion on igneous rocks. So if you recall, igneous processes are one of the really common ways that rocks are originally formed, and we're going to kind of go in reverse this week and talk about the common ways in which rocks are often broken down. And then next week we'll cover sedimentary rocks, which, any sedimentary rock that you might find formed partially as a result of weathering, and in some cases the formation of soils following that weathering. So it's kind of important to keep that context in mind as we move through this chapter 6. So let's sort of zoom into mechanical weathering and chemical weathering a little bit more, because there are a lot of different ways in which mechanical weathering can occur, and also different ways in which chemical weathering can occur. So one of the types of mechanical weathering that occurs commonly in nature is known as frost wedging. And this is really just kind of an alternate freezing and thawing of water in fractures and cracks in the rocks that promotes the further breakdown and disintegration of those rocks. And you can see in this photograph here of this mountain range, which is, primarily rocks exposed to the atmosphere here. This is a really good example of an area where if you have any fractures or cracks in the rocks, then liquid water gets into those fractures or cracks as a result of either rainfall or melting of snow, And then when the temperature changes and that liquid water freezes into a solid or ice, it expands because solid water is less dense than liquid water. And because of that expansion, you have this pressure where you're expanding all of these cracks and fractures within the rock. And in the next slide, I'll show you kind of a tutorial or a more detailed example of exactly how and why frost wedging occurs in these types of environments.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at ice wedging. And after watching the video, you should be able to describe what ice wedging is, why it happens, and its effect on rocks. So let's begin our discussion with this iconic landmark. This is the Old Man in the Mountain. It's in New Hampshire, or I should say it was in New Hampshire. This sort of craggy looking face over here, so the idea is that this looks like a face to some people. That face basically broke off and dropped off the mountain at some point in recent history. And because it dropped off the mountain, New Hampshire lost a vital symbol, but we can take advantage of this because this offers a great lesson in geology. So the basic idea here is the idea of ice wedging. The way ice wedging works is that water expands in volume by 9% when it turns from water into ice. So 9% increase in volume means that the ice basically pushes outward on any sort of container that it's housed in, and that can cause that container to break. So here's a non-geological example, a bottle shattering when the water inside freezes. And you may have experienced this yourself if you ever put a bottle of some beverage into the freezer and then it froze before you had a chance to drink it. Well, the same thing applies to rocks. So high up in the mountains, water gets into little fractures in the rocks. As that water freezes, it pushes outward on those fractures, so it basically enlarges the volume of the fracture, and that can actually serve to make the fracture propagate, so the little tip of the fracture will propagate out and the fracture will get longer, but it will also widen the fracture, and that can cause blocks of rock to go tumbling over the edge. So this happening every winter, tumbling blocks of rock down, you can see that this big giant pile of rock has built up at the base of the mountain. So here's the source for those sediments up here on the mountain cliff, but they end up piling up down below on what's called a talus slope. So this talus slope is made out of boulders that are derived from the cliffs up above it. Now, can that same principle be applied to anything besides ice? Hopefully, the picture here prompted you to say yes. Obviously, tree roots can also penetrate into fractures in rock. And as those tree roots grow, it's not the same as freezing, but they end up basically exerting an outward pressure on that fracture, and that can cause blocks of rock, like this one here, to be popped off the face of that cliff. So root wedging works in much the same way as ice wedging. Both are vital forms of physical weathering. So where does that leave us with the Old Man in the Mountain? Well, that craggy profile that we looked at earlier is actually a function of ice wedging, and the breakdown of that profile was also a function of ice wedging. This was a feature that was both created and destroyed by the same process, ice wedging. Thank you so much for your attention. This has been another Smart Figure.
So on to a few additional types of mechanical weathering. Another type is called sheeting, and this is really the exfoliation, or you can think of it as sort of peeling off of layers of igneous and metamorphic rocks at the Earth's surface as a result of a reduction in confining pressure. What does this mean? It essentially means that when the igneous rock or metamorphic rock formed, it formed deep below the Earth's surface, and so the overlying rock contributed to a fair amount of confining pressure on the igneous or metamorphic rocks that are experiencing sheeting today. So the reason why this occurs is because of weathering. you have the overlying rock being removed, and then rock that's deeper and deeper below the Earth's surface in Earth's past makes its way to the surface, and then all of that confining pressure is gone, which results in fractures in the rock near the top of the remaining igneous or metamorphic rock. And then sheeting can occur, where then gravity causes that fractured rock to fall. Another type of mechanical weathering is salt crystal growth. This one's not quite as intuitive as some of the other types of mechanical weathering to most folks, but an example is if you have like a sea spray or a salty groundwater that penetrates crevices, cracks, and pore spaces in rocks, then as more and more of that sea spray or salty groundwater penetrates those cracks, what's left behind is more of the salt as that water evaporates away or otherwise flows through the cracks. And as those salt crystals grow, you actually get a similar effect as what you saw in frost wedging, except it's from salt crystals that's causing that pressure in the cracks and crevices in the rocks to push outward. And then another type of mechanical weathering is just from biological activity. So this is disintegration of rocks resulting from plants and animals. One example of this that you might think of is if any of you have kind of driven through or hiked through or biked through the Boise foothills, for example, you'll see some exposed granite or granodiorite there. And you might also notice that there are some trees and shrubs that seem to be directly on top of these rocks. Well, a lot of times their roots go through the cracks and fractures in the rocks, and the growth of those roots actually causes mechanical weathering of the rock over time. And similar processes can occur from animals interacting with rocks as well. So this figure shows really a great example of sheeting or exfoliation of a rock. So in this case, the setting is Yosemite, and this particular granite formation is known as Half Dome. If any of you have ever been to Yosemite or are ever interested in checking it out, or at least checking it out online. And so on the left, you can see kind of the process that led to the sheeting at Half Dome and this mechanical weathering that's occurring today. So originally there was a pluton of magma deep below the Earth's surface. I'm in the upper left of this figure right now. And because it formed deep below Earth's surface, there was an immense amount of confining pressure. However, as weathering and erosion of the overlying rock ultimately exposed the once deep pluton to the surface, then that reduction in the overlying pressure causes an expansion of the granite near the granite surface. And then that results in fracturing and sheeting, and then gravity results in some of the sheets of that granite falling down towards the earth. And this is sort of a good textbook example of what sheeting looks like. And on the next slide, I'll show you a tutorial that kind of zooms into this a little bit further.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the phenomenon of sheeting and discover how it forms and what its consequences are. So let's begin our discussion by taking a look at the iconic landmark called Half Dome. This is in Yosemite National Park in California. Basically, there's two things at work here. First off, let's note the scale. There are people here climbing a ladder to give us a sense of scale. Part of Half Dome, basically everything to the right of that line, has been removed by glacial action, and we'll talk about that perhaps in the glacier chapter. However, what we want to focus on right now is this sort of onion skin looking feature here, these flakes that seem to be coming off, and they're all parallel to the sides of this dome, or half a dome. So what's going on here is that Half Dome is made out of granite. Granite, as you know, is an intrusive igneous rock and forms deep underground, so it forms under confining pressure. So there's basically pressure on that magma chamber at the time it intrudes into the crust, and then it crystallizes into igneous rock. So crystals form and it becomes one of these big blobs of igneous rock that we call a pluton. Now, if later on that pluton is brought up to the surface of the Earth, the pressure on it has been released. And as a result of that pressure being released, it actually expands outwards in all directions. So the relief of the pressure basically causes it to increase in volume very slightly. And that increase in volume is actually greater than the strength of the rock. And so the rock tends to break in a series of fractures that are basically perpendicular to the expansion direction. So if it's expanding in all directions, you end up getting this onion skin-like pattern of flakiness on the outside of that pluton. So when you go to Yosemite National Park, you're going to see this just about everywhere you look. You might hike up to view a waterfall, but look beyond the waterfall and you can see all these parallel fractures of rock. These are examples of sheeting. All right, let's quiz you real quick. Which of these two types of rock, intrusive igneous rocks or extrusive igneous rocks, are going to be most likely to experience sheeting when they're exposed at the surface? Hopefully you said the intrusive igneous rocks because they form deep underground under confining pressure. The extrusive igneous rocks wouldn't work because they form at the Earth's surface, so there's no reason for them to expand when they're exposed at the Earth's surface. It's only the intrusive igneous rocks that basically form at depth and then will expand when they're brought to the surface. So an example of an intrusive igneous rock would be a granite. Thank you very much for your attention. This has been another Smart Figure.
So now I'm going to move on to chemical weathering and talk about some common types of chemical weathering and how they impact the Earth's surface and near surface. So again, chemical weathering breaks down rock components and the internal structures of minerals by changing the chemical composition of the rocks themselves. And the most important agent involved in chemical weathering is water, because of the way that water can attack the surface area of rocks. And water is responsible for the transport of ions and molecules that are involved in the chemical processes that transform the chemical composition of rocks during chemical weathering. So, how exactly does water lead to chemical weathering of rocks? Well, one example is carbonic acid. So, carbon dioxide is dissolved in water, and that creates carbonic acid. Why, you might ask, is carbon dioxide dissolved in water? Well, it's because carbon dioxide is in our atmosphere, and when, for example, a raindrop falls towards Earth's surface, it comes into contact with that carbon dioxide, and that carbon dioxide becomes dissolved in the water. It's why if you test the acidity of rainwater, even in locations on Earth where there isn't much manufacturing or anything that would put a bunch of extra carbon dioxide or other things into the air locally, the pH of that water is usually, I think, about 5.6, and 7 is neutral. So generally rainwater is acidic, and generally rainwater is acidic because it contains carbonic acid, or it is carbonic acid in a sense. And carbonic acid dissolves all rocks, but it especially dissolves carbonate rocks. So if you remember from your lab, you probably identified calcite as a mineral, and that mineral ends up being in a lot of carbonate rocks, and that dissolves pretty rapidly from carbonic acid. So if you've ever gone like caving or seen any films or pictures of caves, those are usually composed of carbonate rocks, and the passages through the caves were dissolved by carbonic acid. Another major process of chemical weathering is oxidation. You might be familiar with oxidation when you think of a car rusting or anything made of iron turning red. That is oxidation. But really, oxidation is any chemical reaction in which a compound or radical loses electrons. So that's, for those of you who have taken chemistry, that's what's happening at a chemical level when oxidation occurs. And this is a really important process in decomposing ferromagnesian minerals. So again, ferromagnesian minerals means minerals that contain a fair amount of iron, which is ferro, and magnesium. And so the more mafic minerals are one of the important processes that breaks down the more mafic minerals is oxidation. Again, sort of similar to the reasons why cars rust, for example. It's that iron in the car being oxidized. So I'm going to give an example of chemical weathering of granite specifically as a case study. And I'm going to use granite because it's the most common igneous rock in the continental crust. So how granite weathers, if we're not talking about mechanical weathering, if we're talking about chemical weathering, is that it is chemically attacked by carbonic acid. And so essentially what occurs when a rock is being chemically attacked by carbonic acid is that you have the hydrogen ion within the carbonic acid attacking and replacing other positive ions that exist within the rock. So in granite, for example, you have a fair amount of potassium that exists within the mineral potassium feldspar, and the hydrogen ion from the carbonic acid goes in and attacks and replaces the potassium ions in the potassium feldspar with hydrogen. And then the most abundant product of that chemical weathering of granite, including the breakdown of the potassium feldspar mineral, the most abundant product is clay minerals. And, we'll get into what those are in a second. So, clay minerals are listed in this chart, which is a chart that shows all the really common products of chemical weathering. So as I've tried to explain thus far, chemical weathering is a process where the chemical composition of the minerals within a rock are changed as a result of something occurring, like for example the carbonic acid attacking and replacing some of the elements within the mineral structure. So we'll look at a few common minerals here, and we're looking at minerals because different minerals break down differently remember that all rocks are made of multiple minerals. So when you think about chemical weathering, you really need to think about what's happening at the mineral level, not necessarily the rock level like you would if you were thinking about mechanical weathering. So let's think about quartz. If quartz experiences chemical weathering, the residual product is quartz grains. And this is because quartz is not modified by chemical weathering. It is only broken down into smaller grain size. If quartz is dissolved into water and moved within the water as a solution, then it's known as silica. If we look at feldspars, so for example, on the last slide talking about granite, I talked about the example of potassium feldspar being attacked by carbonic acid as a form of chemical weathering. So the residual products of feldspars like potassium feldspar and plagioclase feldspar are clay minerals, which again I'll get into what exactly clay minerals are a little bit later in this lecture. If feldspars are dissolved in solution, then you end up with silica and potassium and sodium and calcium. And then if you have amphibole, and this includes the mineral hornblende, which you probably identified in lab, you get the residual products of clay minerals and limonite and hematite. And then in solution you get silica and calcium and magnesium. And then finally the mineral olivine, which is a more ferromagnesian mineral that you are more likely to find in something like basalt. You end up with the residual products of limonite and hematite. Or the material in solution will be silica and magnesium. You might notice that the materials that end up in solution or dissolved in the water as a result of chemical weathering always include silica pretty much, and that's because most minerals contain silicon and oxygen. And the result of that, as you'll find when we get into the next chapter on sedimentary rocks, is that a lot of sedimentary rocks are cemented together by silica, because that silica makes its way between the unconsolidated grains of sediment, the sort of quote-unquote residual products, and then precipitates out of solution and then sort of cements that sediment together. But perhaps that's a topic for the next lecture, I guess. Okay, so now we know some of the products that come from chemical weathering. But what are some of the alterations that are caused by chemical weathering? We sort of talked about this with mechanical weathering, about what actually happens to the original rock formations, but we haven't talked about it as much with chemical weathering, so let's get into it. So firstly, you have decomposition of unstable minerals. So, for example, if you have the mineral potassium feldspar in an outcrop of granite and it is exposed to water that has CO2 in it, or it's exposed to carbonic acid, then in that condition the potassium feldspar is unstable and it's broken down. And in that process you generate materials that are stable in that environment. So on the last slide, all the products that we looked at, the products of chemical weathering, those are the minerals that are actually stable in the environment that they're in, which is at the surface, potentially being exposed to water, etc. And you also have physical changes to the rock as a result of chemical weathering, such as the rounding of corners or edges, um, or in some other cases, spheroidal weathering. So this diagram in the lower right of the slide kind of shows an example of how these physical changes to the rock can occur from chemical weathering, sort of step by step. So you can see kind of in the upper left of that diagram, you have rock that is extensively jointed, perhaps because of that release of the confining pressure as the overlying rock erodes away, and this rock becomes exposed to the surface and then fractures from that release of confining pressure. And then after you have those fractures and joints, water may seep into the fractures and joints, and it decomposes minerals. We can go back to potassium feldspar as one example, and then enlarges the fractures and joints within the rock. And then the rocks are attacked more and more because there's a greater amount of surface area available for chemical weathering to attack. And that creates a situation where you start to have rocks break away from the larger formation, and the corners and edges start to take on a spherical shape. In extreme cases, like for example here in the picture on the right in Joshua Tree National Park, you end up with spheroidal weathering, where not only are the edges of the rock rounded from chemical weathering, but you end up with a bunch of rocks that look almost like spheres.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at spheroidal weathering. And after you're done watching the video, you should be able to describe what spheroidal weathering is, what it looks like, and how it forms. Here's a look at a scene you might encounter if you ever visited Joshua Tree National Park in Southern California. There in the Mojave Desert, you'll find a granite that has been broken along a series of fractures. So we would call these fractures joints, perhaps. And these joints divide the granite up into a series of angular blocks. So you can see these blocks, for instance, over here on the upper left, they have sort of a diamond shape overall. But not all of them have that shape. For instance, over here in the upper right, you see some that have sort of a rounded form. In the foreground, there's two very nice boulders that have a very rounded shape to them. And up here at the top, you can see there's one that's almost perfectly spherical. So what's going on with this? How do we explain this disparity between really angular blocks of granite and really round ones? Well, it goes back to what we were discussing in another Smart Figure, that basically the increase in surface area of rock due to physical weathering ends up producing more area for chemical weathering to attack. So let's go ahead and just zoom in here on the first block in this diagram. You'll notice that this block is a cube of rock, not quite a diamond like the ones we were just looking at, but close enough. And it's got 6 faces. The corners basically have the greatest amount of surface area of any of the faces on the block. So that basically they're exposed on the top, the left, and the back, if you want to think about it that way. And that's more area for chemical weathering to attack. So what that means is that the corners are going to tend to wear away faster than the rest of the rock. So we're going to eat away at these corners more rapidly than we would eat away, say, at the middle of these faces. So how does that relate to the scene we looked at in Joshua Tree? Well, it'd be something like this. You've got an initial situation where you have granite. That granite is being physically weathered, so it's being broken into a smaller number of pieces. Those are the angular blocks. Then weathering goes to work on those angular blocks, transforming the ones with really sharp corners into increasingly rounded shapes. And then basically that's exposed at the surface, and that's the scene that we were looking at. So the overall trend here is basically to go from an initial angular block of a greater volume and then wearing away the corners more rapidly, and after the corners, the edges more rapidly. And over time, that'll basically reduce that initial cube into something that is increasingly spherical. So the end result basically is a sphere, and a sphere is the most efficient shape in terms of surface area to volume. So it's got the least amount of surface area for a given volume of rock. Now, is spheroidal weathering the only way that you can produce a rounded boulder like this? Hopefully you answered no. This will be a concept that we cover in the next chapter, but you can produce a rounded shape also by basically tumbling an initial angular block downstream or over and over in a surf, and you basically will break off the little pointy bits that poke out, and you'll get a rounded shape that way. So in summary, there are two ways to produce a rounded shape geologically. You can produce it through tumbling of the cobble over some distance, or you can weather it in place, and that's spheroidal weathering. Thank you very much for your attention. This has been another Smart Figure.
So now that you hopefully understand a little bit about mechanical weathering and chemical weathering, I'm going to talk a little bit about the rates of weathering. So we've talked about the different ways in which rocks can be broken down in the natural world, but how fast does this happen, you might wonder, and what conditions govern how fast rocks break down. So the factors that affect weathering rates include the characteristics of the rocks. So, for example, rocks containing the mineral calcite, which is in the sedimentary rocks marble and limestone, readily dissolve in weakly acidic solutions, so that weak carbonic acid caused by CO2 dissolved in rainwater, for example. And then if you have silicate minerals, which again are very common in the continental crust, and they weather in the same order as their order of crystallization. Sorry. So if you go back to the chapter on minerals earlier in this course, and in the chapter on igneous rocks, and you think about Bowen's reaction series and how some minerals precipitate out of the magma and form at hotter temperatures, and some precipitate out of the magma and form at colder temperatures. The silicate minerals basically weather in that same order. One way that I like to think about this is that the conditions at Earth's surface are much different than the conditions are far beneath the Earth when these minerals form. And so if a mineral is forming when temperatures are extremely hot and pressure is extremely high, then that mineral is more likely to be more unstable at Earth's surface. And therefore it would weather faster than minerals that formed when the body of magma that they formed from was cooler in temperature later on. And so I think sort of thinking about the reason why certain minerals weather faster than others, and thinking about how far the conditions are at Earth's surface from the conditions that existed when they formed, is a good way to kind of conceptualize this, and it helps you to understand why some minerals weather faster than others.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the different variables that influence the rate at which rocks will chemically weather. Let's begin our discussion with a look at two tombstones found in the same cemetery. The tombstone on the left was erected in 1868, the tombstone on the right, 1872. The one on the right is younger by a good 4 years. However, you can see that the one on the right does not look very good. It's not standing the test of time very well. whereas the one on the left is standing the test of time pretty darn well indeed. You can still read the inscription and everything. So what's the difference here? The one on the left is made of granite, a rock that's dominated by quartz and potassium feldspar and some plagioclase feldspar too. So basically that's made out of minerals that are either stable or metastable in the environment of Earth's surface. In contrast, the example on the right is made of marble. Marble, of course, is dominated by the mineral calcite, and calcite is not only much softer than quartz or feldspar, but it is also chemically more susceptible to being dissolved away by weakly acidic rainwater. So the material that a tombstone is made from ends up mattering. And this is a good lesson for understanding the rate at which rocks weather. Composition matters. Here's a look at some of the results of different compositions weathering under the same conditions. This is shiprock in New Mexico. We've looked at shiprock in another smart figure. You can see the central volcanic neck here that used to be at the heart of a composite volcano. And then there's a very prominent dike where igneous rock has filled in a crack in the surrounding rock. There's another dike over there. And those igneous rocks are basically standing up tougher to weathering than the surrounding sedimentary rocks they cut across. So all the rock around them is weathering away at a faster rate, and as a result, the igneous rock pokes out of the landscape because it's weathering away more slowly. That's called differential weathering. Another example of differential weathering can be found in the Appalachian Mountains of the eastern United States. We're looking here at the Valley and Ridge Province, in this case in Pennsylvania, where actually they call it the Ridge and Valley Province. But you can see here that we've got alternating ridges and valleys. Ridges and valleys. And so the reason we've got ridges and valleys there is that the ridges are held up by very quartz-rich sedimentary layers, sandstones and conglomerates, whereas the valleys are underlain by shales and limestones, rather weak layers that don't stand up as well to weathering. So that's another nice example of differential weathering. Another variable to consider is climate. You're looking here at a gully eroded into laterite. Laterite is a bright red tropical soil. Warmer, wetter climates tend to produce faster rates of weathering than cooler or drier climates. So the water helps facilitate all kinds of chemical reactions, dissolution, hydrolysis, and oxidation. And then the temperature, of course, provides the energy to run those reactions. So higher temperatures have more heat energy, and the opposite, of course, will be true in a colder environment. So one of the review questions at the end of the chapter basically asks you to imagine a block of granite looking like the one on the left there, and then imagine that granite going into two different scenarios. One is we take that block of granite and we stick it in one of the dry valleys of Antarctica, or we can stick it in a jungle in some place like Costa Rica. So let's first consider the scenario where we put it in this dry valley of Antarctica. What do you think is going to happen to it there? Okay, hopefully your answer is not much. Basically, because that is a very cold environment and a very dry environment, it is called the dry valleys after all. There's not a whole lot of precipitation there. You are not going to expect much to happen to that granite. It's going to have a very slow rate of weathering. In fact, some of these blocks of granite here may have been there for millions of years. On the other hand, if we put that same block of granite in very different climatic conditions, such as in a warm, wet climate like the one pictured below, we would expect it to rot pretty quickly, to fall apart. So the ferromagnesium minerals are going to end up oxidizing, the feldspars are going to end up undergoing hydrolysis and producing clays, and then as the rock loses its structural integrity, physical weathering will take over and it will be broken up into smaller and smaller pieces. Thanks very much for your attention. This concludes yet another Smart Figure.
So there are a few other factors that I should talk about in relation to the rate of weathering. And one is climate. So specifically the temperature of the atmosphere and the moisture levels in the atmosphere are the most crucial factors. So it turns out that chemical weathering is the most effective or fastest in areas that are warm and moist, and chemical weathering is less effective and slower in areas that are cool and dry. And the reason for this is that moist climates have more water, and water catalyzes a lot of chemical weathering, and warmer climates catalyze faster chemical reactions, and Faster chemical reactions result in more effective and efficient chemical weathering. Another factor that affects chemical weathering is the concept of differential weathering. And differential weathering basically means that masses of rocks do not weather uniformly because of regional and local factors. Local factors might be there's a higher concentration of some mineral in part of a granite formation than there is in another part of that same granite formation. And a regional factor might be that the granite in that area formed in a different way than most granite does. So, like for example, the reason why the granite structures in Yosemite, like Half Dome that we saw earlier in this lecture, are so crazy high and look so unique is because that granite had a different process of formation than most granite. And differential weathering results in kind of unusual and spectacular rock formations and landforms because you have different types of rocks or rocks that have been impacted by a different phenomenon right next to one another, and that causes the rate of weathering to be really fast in some places and really slow in some places, and you can see that juxtaposition firsthand. Let me show you an example. So this is a really good example of differential weathering here. I don't recall where exactly this is, but you can see it's interesting, like the tops of a lot of these structures that you can see are much larger than lower down in the structures, and that's because that layer of rock is more resistant to weathering than the lower layer of rock. And it results in these pretty crazy structures. So anytime you see something like this, it's not because the wind or the water necessarily is doing something completely out of the ordinary. A lot of times it's actually because the different layers of rock are more resistant or less resistant to weathering.
Hello, I'm Michael Collier. Rocks don't last forever. They break down, they weather at the Earth's surface. That's the misty Badlands down there. It's a moonscape in northwest New Mexico. It's a great place to get a bird's eye view of rocks being sculpted by weathering. On this field trip, we're going to look at strata that were deposited during the time of the dinosaurs. Different layers within these sedimentary rocks weather away at different rates. The result is this wild collection of unexpected shapes. We'll learn that weathering is caused by mechanical or chemical forces. Water, fire, even human beings can hasten the processes of weathering.
The Bisti lies 30 miles south of Farmington in the heart of the San Juan Basin. These 75 square miles of the Fruitland and Kirtland formations are filleted open, mostly by water, sometimes by wind, exposing 70 million-year-old sedimentary rocks, sandstones, shale, and mudstones. During the late Cretaceous, an inland sea occupied this part of North America. Rivers and deltas on the edge of the seaway were home to fish, turtles, crocodiles, and early mammals. How many of those animals do you think you would recognize today? The Fruitland Formation is riddled with fossilized bones as well as petrified wood. The overlying Kirtland Formation is busting its buttons with dinosaur remains. Now, as layers of the Bisti are peeled back, bones are exposed. In fact, a new species of Tyrannosaurus was excavated here not long ago. Bisti Badlands sits 6,000 feet above sea level. Winter nights are cold, but there's plenty of sunlight to raise daytime temperatures. Any water that creeps into rock crevices, repeatedly freezes and thaws, expands and causes cracking in a process called frost wedging. Blocks are pried into smaller, angular pieces, a type of mechanical weathering. When minerals that form deep underground become exposed at the surface, they must adjust to new conditions of lower pressure and temperature. Exposed to the sun, or soaking in the rain, rocks begin to disintegrate. Feldspar crystals decompose into clay. Quartz crystals break down into grains of sand. The Bisti is a stark desert, but a few springs do flow here periodically. Salts can be dissolved in the water and then deposited into crevices. As salt crystals grow, they enlarge cracks in the rock and, like freezing water, break it apart. Also, chemical weathering is greatly accelerated by the presence of acid in groundwater. This might happen when rain mixes with carbon dioxide from the atmosphere to form carbonic acid, or when minerals like pyrite decay into sulfuric acid. Can you think of other examples of acid hastening weathering? The Fruitland Formation is a stack of hard and soft layers, sandstones on top of shale, mudstones on top of coal. Sometimes a strangely shaped hoodoo forms when a cap of sandstone shields the underlying shale from rain. In this way, sandstone and shale, crumbling at different rates, exhibit differential weathering. Weathering and erosion are separate processes. Weathering breaks rocks down. Then erosion, powered by water or wind, carries grains away. But the two can be intertwined. As erosion carries away particles of rock, fresh exposures are subject to renewed weathering. A surprising variety of agents cause weathering. Animals can be prodigious burrowers, busting rocks apart as they dig. Fire is another agent. The Fruitland Formation is riddled with coal seams, some of which burned while still underground. Nearby layers of siltstone were baked and broken into red clinkers. In the last few hundred years, humans have become significant agents of weathering. It's true that the Bisti Badlands are a protected wilderness, but by conservative estimates, the Fruitland contains 90 million tons of coal, a fact not lost on power companies who would burn it to generate electricity. When miners dig up the coal, they also cause weathering. Can you think of other human activities that might influence weathering on a geologic scale? Which term best describes the process that created the oddly shaped rocks at Bisti Badlands? Unloading? Differential weathering? Exfoliation? Rocks at Bisti Badlands were created by differential weathering. How can plants facilitate weathering? As roots grow, they're able to exert tremendous pressure, enough to break rocks. This is an example of mechanical weathering. But plants can also increase the acidity of groundwater, which leads to chemical weathering.
So, now that we've talked pretty extensively about mechanical weathering and chemical weathering, and why the rates of weathering differ, and what happens to the Earth's surface and rocks, etc., as a result of different types of weathering and different rates of weathering, it's important to talk about some of the products of weathering, which we already talked about some of the specific products of weathering in terms of like clay minerals and silica, etc. But we didn't talk about soil, which is usually what you get as a result of multiple products of weathering that come together in a particular environment. So what soil really is a combination of mineral and organic matter, water, and air. Or that portion of the regolith, which regolith is rock and mineral fragments produced by weathering, that supports the growth of plants. And it can only support the growth of plants if you have that mineral matter, organic matter, water, and air. So this diagram on the right here next to this person shoveling soil shows a good example of what the percentages look like in a good soil that supports the growth of plants. So about 45% mineral matter, or matter that was weathered from a parent rock, and then about 25% air, 25% water, and about 5% organic matter. Where does the organic matter come from? It comes from other life forms decomposing primarily. So now that you hopefully understand what soil is, let's talk about some factors that control soil formation. So obviously soil is the result of weathering of a rock or rocks, and then erosion of that material to a new location to form the soil. So when we think about factors controlling soil formation, we need to think about how the soil came to be in the location that we are interested in. So we need to think about the parent material. So the term residual soil refers to soil that comes from the underlying bedrock, or the parent material is the underlying bedrock. So for example, if you have a slab of granite that is exposed to Earth's surface, and then weathering of that slab of granite, and then erosion of those weathered materials results in a soil on top of the granite. That is a residual soil. In contrast, a transported soil forms in place on parent material that has been carried away from elsewhere and deposited. So this means, for example, if you are adjacent to a river and you're farming the soil next to the river, that soil was likely carried by the river or transported by the river away from the parent material to arrive at that location, and then was deposited. So that's a transported soil. And these two different types of soils generally have kind of different characteristics from one another, because the residual soil is going to kind of closely resemble the chemical composition of the bedrock, whereas the transported soil is probably a more well-mixed soil that was sourced from a variety of different locations. So some other important factors that control soil formation are time and climate. Time really is important to all geological processes, and is an important variable to think about when we're discussing any geological process as a result of that. So the amount of time that it takes for soil to form varies for different soils depending on geologic and climatic conditions. So we just talked about soil that forms directly on top of the parent rock versus soil that forms from being transported away from various parent rocks. However, climatic conditions also play a role. In fact, climate is the most influential control of soil formation, and key factors are temperature and precipitation. So this is similar to how temperature and moisture are controlling factors on the rate of weathering. They're also controlling factors on soil formation, as you might imagine. A couple more factors that control soil formation. So as you can see, there are a number of factors. It's kind of a complex series of processes that lead to soil formation. So you have plants and animals, and this is because organisms influence the soil's physical and chemical properties. So for example, if you have plants decomposing a lot in an area, then that adds more organic material to the soil, or plants' roots can add structure to the soil, and then burrowing animals can aerate soil, for example. And then topography. So as you probably have noticed, maybe you haven't noticed that you've noticed this, but if you look at really steep slopes, so think about maybe like the Sawtooth mountain range up near Stanley, those slopes usually have really poorly developed soils. They're just too steep, and so gravity and weathering and erosional processes usually transport any soil that might form away. The optimum terrain for forming good soil that can support plant life is really a flat to undulating upland surface. And so that is why flat and undulating terrain is usually where you would find agriculture, and why you oftentimes have kind of lush green valleys between the mountaintops and the river bottoms that or the rivers that are cutting through the valleys. So this figure shows some good examples of soil development. So on the left, you can see that there's no soil development in this mountainous terrain with extremely steep slopes, for reasons which I just described on the last slide. This actually looks like the Sandias, which are just east of Albuquerque. I lived in Albuquerque for a couple of years when I worked for the U.S. Geological Survey, so it feels very nostalgic there. And then you have an example of transported soil developed on unconsolidated stream deposits to the right of that. So if you imagine the soil that may have formed from near those very steep slopes kind of being washed down into the valley from wind and water, and in this case primarily water because these are stream deposits, then again that's usually the type of area that you would have a good opportunity for agriculture, as you can see in that photograph there. And then further to the right, you can see sort of an example of a plateau on the other side of the stream valley here, where the soil is different because it's a residual soil that's developed on the bedrock. And in this case, the soil isn't transported away from where it forms nearly as easily because the slope isn't nearly as steep. It's more of a plateau, right? So the forces of wind and water remove the soil at a much slower rate, and in fact the roots of all of the plant life growing there tends to hold that residual soil in place to a pretty great extent in this particular example. So now that hopefully you have kind of a picture of how soils develop differently in different environments, as a result of weathering and erosion and transportation of mineral matter and organic matter and mixing of water and air with that. It's important to kind of look at an idealized soil profile to just talk about the different layers that naturally form within a soil column, and why those different layers tend to exist in those positions or in the soil column fairly often in the natural world. So kind of moving from top to bottom, so land surface down to the bedrock. First we have the O horizon, which is a soil layer that's usually pretty thin and is made of loose and partly decayed organic matter. So if you imagine leaves falling, pine needles falling, and things like that, and kind of falling on the land surface and decaying over time, and those materials being partly decayed, that's pretty much what the O horizon is. And below that is kind of what people typically think of as soil, which is the A horizon. And this is mineral matter mixed with some humus. So the humus is, basically organic matter that is more fully decayed than it is in the O horizon. And this mineral matter, it doesn't really matter whether it came from the parent material locally or was transported to that location from elsewhere. In either case, it is still the A horizon. And this is the area of the soil that plants would typically root into to get water and nutrients, because this is the area of the soil that typically holds on to nutrients and water the best, at least as it relates to the ability of plants to access that water. So, that mixture of mineral matter and organic matter and water and air that we talked about earlier in this lecture. Below the A horizon, you have the E horizon in this example. And this is kind of the zone of leaching, meaning that any water that infiltrates down through the soil profile, like past the A horizon, and gets to this E horizon, may start to leach those nutrients, and that is why this area of the soil column is less desirable for plants, is because you don't have the nutrients there that you might have in the A horizon, which is usually kind of a younger soil, right? Once you get down to the B horizon, this is kind of known as a subsoil, and this is an area where you have an accumulation of clay transported from above. So part of that leaching that goes on in the E horizon is that, for example, feldspar minerals that were in the E horizon are chemically weathered as a result of water moving down through the soil column, and then that results in that feldspar being broken down into clay minerals that are then leached further down into the B horizon, or this subsoil as it's called here. Finally, if you get down to the C horizon, that's kind of the partially altered parent material. So you can think of it as like super young soil that's kind of a mixture of bedrock that hasn't really been weathered yet, and bedrock that has been more weathered, that's like formed into a more legitimate soil. So that's why that The sea horizon is generally referred to as partially altered parent material because some of it's been altered and some of it's still pretty raw, similar to the bedrock. So now I'm going to move on to kind of a description of this soil profile in greater detail and a better description and more detailed description of how all these different layers in the soil form and interact with one another. So thus far, we've talked pretty much about how the natural environment uh, causes weathering of rocks and the formation of soils. Um, However, it's also important to talk about anthropogenic impacts on soil. So anthropogenic just being meaning as a result of human activities. Because we have a really massive impact on soil, and it's important to understand this, not only what our impact is, but how to mitigate those impacts as well. So I think it's obvious to a lot of us that the agricultural productivity of soils can be improved through fertilization and irrigation. This obviously isn't necessary in all locations, but in a lot of locations, if you kind of add nutrients and or water to your soil, you're going to have a more productive agricultural plot. However, unfortunately, soils can be damaged or destroyed by irresponsible agricultural practices, including irresponsible application of fertilization and of fertilizer and irrigated waters. And this is unfortunate because soils are really crucial for providing food, fiber, and other basic materials to humans and other animals, and simultaneously are one of the most abused natural resources that we have. And I think most of you can probably intuitively understand why that is, because soil is right at the surface of the earth, so it's pretty easy for us humans to disrupt. So thinking about anthropogenic impacts on soil within a case study of what happens to soil when humans clear a tropical rainforest. So usually when people think about clearing tropical rainforest, they think about, taking out all these trees that are habitat for, all the local animals and other types of plants. Maybe impacts on the carbon cycle that are caused by removing a bunch of trees that are storing carbon. But there's also a pretty profound impact on the soil when you do something like remove a tropical rainforest. And just for context, usually tropical rainforests are cleared for logging and agricultural use. So a lot of times the wood that comes from these rainforest trees is really expensive on the open market, and so you can sell it for a lot. And then also, if you clear that land, you can use it to grow vegetation or conduct ranching activities, or both. So that's usually why it's done. However, the soils beneath the trees in tropical rainforests are typically poor in nutrients and unsuitable for agriculture after you clear the trees. And the reason why this is if we think back to that idealized soil profile and we think of the zone of leaching, well, in a rainforest, you have so much water moving down through the soil that really a lot of minerals that would provide nutrients in other environments are leached because there's so much water moving through, and you have that warm, moist environment that we talked about that is just like ripe for a fast pace of weathering. And so that leaves you with soil that's poor in nutrients. And to make matters worse, most of the nutrients that you do find in tropical rainforest soils are from the trees. So if you clear the trees, then the mechanisms which were previously providing at least some nutrients to the soil in that area is gone. And then also clearing tropical rainforests promotes soil erosion. So a lot of times in tropical rainforest, really what's holding this leached, sometimes deep soil profile in place, especially on steep slopes, are the roots of these trees. And so unfortunately, a lot of times you clear these trees for agriculture, and then if the slope is steep at all, that soil might just get washed away and go down valley in a stream really quickly afterwards. So this photograph here is an example of what it looks like, what the soils look like after you clear trees in a tropical rainforest. And I don't know how many of you are farmers or know some farmers, but that doesn't look like very good agricultural soil. It's very loose, looks like it's very easy to erode, and that sort of orangish color that you have there is kind of indicative of all the leaching and weathering. You know, you can see some of the iron oxide in that orange color from the oxidation of the iron-bearing minerals in the soil as well. So, you know, speaking of soil erosion is obviously a natural process within the rock cycle. And, you know, erosion rates of soil are dependent on climate, slope or topography, and the types of vegetation, because plant roots kind of hold soil in place. However, human activities such as deforestation and farming practices can enhance soil erosion. And one of the reasons is, as I mentioned before, you're kind of removing those roots that are a stabilizing force for the soil, and kind of removing their protection from wind and water, weathering and erosion. However, there are ways that one can farm or ranch in a more conservative way to protect soils. So a couple different ways, just quick examples are this photograph on the left. You can see kind of these strips in the hillside of agricultural plots, and then just grasses in between those agricultural plots. So the grasses you can see are perpendicular to the angle of the slope. So in this case, that pattern of having an agricultural plot and then grasses over and over again reduces soil loss because it slows the runoff of irrigation water. And then on the right, you can see that even if you have a grass waterway that is parallel to the direction that irrigation water would be draining from a field, that grass still prevents the formation of gullies, and kind of traps soil washed from the crops in the grass, sort of maintaining it in the agricultural field and not allowing it to run off. You'll notice in Idaho that a lot of agriculture doesn't look like this, and a lot of ranching doesn't look like this. And a lot of Idaho is a semi-arid environment, and what you end up with is a lot of sedimentation, or a lot of areas where unfortunately farmers lose a lot of soil, and then that soil ends up in our stream system. And if you get too much soil in your streams and rivers, some ecosystems like our salmon runs are disrupted like that, because it's harder for salmon redds to survive when they don't have as much access to oxygen because they're buried in sediment, for example. So, you know, this is kind of something to to keep in mind is that there are responsible and irresponsible ways not only for us to farm the land and ranch the land, but also in terms of our urban development. A lot of times, the way that we develop our cities, we don't really think about the erosion of our soil and the impact that that might have in the long term. But soil is such an important resource for life that it really needs to be considered in all aspects of land management. So one last thing that I wanted to discuss in relation to soil is kind of the concept of weathering leading to deposits of ore that are valuable for humans. So weathering creates deposits of ore by concentrating metals into economically valuable concentrations. This is known as the process of secondary enrichment. Secondary because you already have the soils deposited that contain these metals, and then they are enriched after the fact by weathering. So a couple examples of this are the mineral bauxite, the rock bauxite, which is a principal ore of aluminum, often forms in rainy tropical climates from chemical weathering and the removal of undesirable elements from the soil by leaching. And so this is an instance where you actually have an ore of aluminum being formed by weathering and by leaching of aluminum, forming more concentrated deposits of that resource. And then there are also instances where weathering processes concentrate metals that are deposited through low-grade primary ore. So common examples of this are copper and silver, which are obviously both pretty useful to humans as well. And this process typically occurs in deposits containing pyrite. Pyrite in and of itself is kind of a low-grade ore, meaning it doesn't contain a high concentration of copper or silver. But when pyrite is exposed to weathering, a lot of times that weathering results in more concentrated pockets of copper and silver that can be mined in a more cost-effective way. All right, everyone. Thanks for listening. I hope you enjoyed, and I hope I see some of you in the live Zoom lecture this week so that you can ask some questions in real time. I think that other students being able to see what sort of questions you are asking will be beneficial to the whole class as well. So hopefully this experiment works out. And this one bullet point that I had on this slide is more a joke than anything, but I guess I was just thinking about what the weather forecast looks like in Boise this week, and then this whole lecture was on weathering, and I was thinking about what if we had weathering forecasts for people that were interested in how rocks were being broken down in the local area each week. And so I don't know, it's kind of a joke, but it's kind of interesting to think about. It's kind of a wet and cold environment out there right now, so moderate weathering, I suppose, but probably a fair amount of chemical weathering from carbonic acid in the snowmelt. Anyways, that's enough of that, and hopefully I'll talk to you soon. Have a great week.